In this video, we are solving exponential equations, and we have the equality property for exponential equations, and it says if b is a positive number other than 1, then b raised to x and b raised to y can only be equal if x is equals to y. Since you can see the bases are the same, so the only way for these two to be equal, x has to equal y. And you can see this example, 3 raised to x, then if you're told it's equal to 3 raised to 5, then x has to equal 5. And here we have an example, and we have the steps to do it. So we are told to solve for x. So let's work it out. So here, I just need to make sure the bases are the same. Because if the bases are the same, then I can equate the exponents. So this is 7 squared 2x 2x plus 1, and then I just equate the exponents. So this is 3x plus 4. I'm going to distribute the 2, so this is 4x plus 2, and then when I solve this equation, I'll get x is equals to 2, and that's the answer. Now the next one, this is going to be 3 raised to 4, and this is 3 minus x. On the other side, remember I can use the properties of exponents to like the reciprocal of 3. So 3 minus, so I'm going to multiply everything here by minus so that I can move the 3 up, just like on the other side. So then I get 4x, I distribute the 4, so 12 minus 4x is equals to negative 5x plus 6. And then I just need to solve this equation. And when I solve this equation, I'm going to get x is equals to negative 6. Okay, now this one, you always want to make sure your bases are the same. So what I'm going to do is to make that the 6 have the same bases. The other one, the right hand side. So this is going to be 6, 2, x minus 9 is equals to 6, 2x. So this is 2x minus 18 is equals to 2x. When I subtract 2x, then I'm going to get negative 18 is equals to 0, and that's not true. So that means this one is a no solution. In this example, I'm going to solve exponential equations with different bases. And here is an example. And I have 3 raised to x is equals to 14. So normally, I would check to see whether I can write 14 to the same base as 3. But that's not possible. And this is where I use the properties of logarithms to isolate x. So what am I going to do? I'm going to write logarithm to base 3 of 3 raised to x, and I do the same on the other side, logarithm to base 3 of 14. And see, when I do this, I'm able to isolate the x, and I get x is equals to logarithm to base 3 of 14. And then I can simply put this in the calculator, and this gives me 2.4. And just in case you don't have a calculator which allows you to use any base, you could use the change of base formula. So for this one, you could do logarithm of 14, logarithm base 10 of 14, logarithm to base 10 of 3, and they should give you the same answer. Okay, now let's go to the next one. So here, the first thing would be to add 2 to both sides. So I get 2x is equals to 10. Then I'm going to introduce the base. So logarithm to base 5 of 2x is equals to logarithm to base 5 of 10. And this gives me, see, this helps me to isolate the x. So, but actually here I have 2x is equals to logarithm to base 5 of 10. So x is going to be logarithm to base 5 of 10 divided by 2. And when I put this in the calculator, I get 0.7. So that's going to be the answer. So another example here. So the first thing is I subtract 1. So then here I get 5 raised power e of x is equals to 15. I can divide by 5. Then I get e raised to x is equals to 3. And what do I do with this? I need to introduce a base which will help me isolate x, and this is where I use the natural logarithm. So natural logarithm e of x is equals to natural logarithm of 3. This helps me to isolate the x. So because here I get x is equals to natural log of 3, and the natural log of 3 is the same as 1.1 when I put that in the calculator. So x is the same as 1.1. Okay, now let's do the other one here. So we have 6x minus 10 is equals to 9. So I can add 10 to both sides. And what do I get? 6x is equals to 19. And then I'm going to introduce logarithm to base 6 of 6x is equals to logarithm to base 6 of 19. Okay, so now see, this is all gone. So I have x is equals to logarithm to base 6 of 19. And remember, you could use a change of base formula or just put this in the calculator. If you don't have a calculator with base 6, you could do logarithm to base 10 of 19, which is just what your calculator has, over logarithm to base 10 of 6. And when you do that, you get approximately 1.64. Okay, another example here. So this is going to be logarithm to base 11 of 11 raised to 5x is equals to logarithm to base 11 of 33. So see, this is going to be gone. So we get 5x is logarithm to base 11 of 33. I divide by 5. So I get x is equals to about 0.29. And that's going to be the answer. And the last example I'm going to do here, I introduce the natural logarithm of e x plus 2. I do the same on the other side, natural log of 10. So this becomes, see, this is all gone. X plus 2 is equals to natural log of 10. Then I subtract 2 from both sides. So I get natural log of 10. And then I'm going to subtract 2. And when I put this in the calculator, I get approximately 0.303.